determine the appropriate overcurrent protective device size for a fan terminal unit, start by determining the apparent power in volt amps. The total volt amps for the unit is 3 kVA per leg, multiplied by 3 legs, which equals 9 kVA. The volt amps for the motor is 1.127 kVA. Next, calculate the current in amps. The phase current for the unit is the volt amps divided by voltage times the square root of 3. This is 3 kVA divided by 480 volts times the square root of 3, which equals 3.54 amps. The phase current for the motor is volt amps divided by voltage, which is 1.127 kVA divided by 277 volts, which equals 4.7 amps. Now determine the required circuit breaker size. Since one phase will carry more current than the other due to the motor load, the circuit breaker must be sized to handle the higher current. The total phase current with the motor load is 3.54 amps plus 4.7 amps, which equals 7.61 amps. Select the correct overcurrent protective device size. The overcurrent protective device size should be the next standard size breaker above the calculated current. In this case, a 15 amp circuit breaker is the appropriate choice. It is important to consider other factors. The circuit breaker should also be rated for the appropriate voltage, 480 volts. The overcurrent protective device should be installed on the line side of the motor starter for the motor. The motor starter should be sized and selected according to the motor's specifications. Firstly, let's delve deeper into calculating the apparent power. This involves understanding the volt-ampere relationship in a three-phase system. When dealing with balanced three-phase loads, you can determine the total apparent power by summing the apparent power of each phase. In situations where the load is unbalanced, such as when a single-phase motor is connected to one of the phases, you need to account for the individual phase loads separately. Secondly, we need to break down the current calculations, starting with the line current for the fan terminal unit itself. The formula used, volt amps divided by voltage times the square root of 3, is fundamental for calculating the current in a balanced three-phase circuit. The square root of 3 accounts for the phase difference in a three-phase system. This calculation assumes a balanced load, where each phase draws an equal amount of current. For the motor, the current calculation is simpler since it's a single-phase load. The formula is volt amps divided by voltage, directly giving you the current drawn by the motor. Thirdly, it is important to explore the selection of the overcurrent protective device. Selecting the right overcurrent protective device involves understanding its purpose, which is to protect the circuit from overloads and short circuits. The overcurrent protective device size should be slightly higher than the calculated full load current to avoid nuisance tripping, but not so high that it fails to protect the circuit in case of an overload or short circuit. The National Electrical Code provides guidelines for selecting the appropriate overcurrent protective device size based on the type of load and the conductor size. Fourthly, let's discuss the additional considerations more thoroughly. The voltage rating of the circuit breaker is crucial. The breaker must be rated for at least the system voltage, which in this case is 480 volts. Using a breaker with a lower voltage rating can lead to failure and pose a safety hazard. The placement of the overcurrent protective device on the line side of the motor starter is important for protecting the motor and the motor starter from overcurrent conditions. The motor starter, which includes components like contactors and overload relays, needs to be properly sized to handle the motor's starting and running current. The overload relay is specifically designed to protect the motor from overheating due to overloads. Fifthly, one should consider the type of overcurrent protective device. Common types of overcurrent protective devices include circuit breakers and fuses. Circuit breakers are resettable and can be tripped manually for maintenance purposes. Fuses are one-time use devices that must be replaced after they blow. The choice between a circuit breaker and a fuse depends on the application and the specific requirements of the system. Sixthly, it is important to address harmonics. In modern electrical systems, nonlinear loads such as electronic ballasts and variable frequency drives can introduce harmonics into the system. Harmonics are currents and voltages at frequencies that are multiples of the fundamental frequency, which is typically 60 Hz. Harmonics can cause overheating of equipment, voltage distortion, and other problems. To mitigate the effects of harmonics, you may need to use harmonic filters or other mitigation techniques. Seventhly, think about voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the system. The National Electrical Code provides guidelines for limiting voltage drop in branch circuits and feeders. To minimize voltage drop, you can use larger conductors or reduce the length of the circuit. Eighthly, consider short circuit current rating. The short circuit current rating of an overcurrent protective device is the maximum current the device can safely interrupt without failing. It is important to ensure that the overcurrent protective device has a short circuit current rating that is equal to or greater than the available short circuit current at its location. Failure to do so can result in the overcurrent protective device failing to interrupt a short circuit, which can cause significant damage and pose a safety hazard. Ninthly, one has to understand the ambient temperature. The ambient temperature can affect the performance of overcurrent protective devices. Overcurrent protective devices are typically rated for a specific ambient temperature, and their current carrying capacity may need to be derated if the ambient temperature is higher than the rated temperature. The National Electrical Code provides guidelines for derating overcurrent protective devices based on ambient temperature. Tenthly, think about coordination and selectivity. Coordination and selectivity refer to the ability of overcurrent protective devices to trip in a coordinated manner, so that only the overcurrent protective device closest to the fault trips, minimizing the disruption to the rest of the system. This is typically achieved by using overcurrent protective devices with different time current characteristics. The National Electrical Code provides guidelines for coordination and selectivity. Considering all these factors ensures the safety and reliability of electrical systems. It's not just about picking a breaker, it's about understanding the entire electrical landscape in which that breaker operates. By paying attention to these details, potential problems from nuisance tripping to catastrophic failures can be avoided. The selection of a 15-amp circuit breaker is a starting point. The choice hinges on understanding the electrical characteristics of the fan terminal unit and its operating environment. Therefore, thoroughly understanding the electrical system and its components is vital for making informed decisions that ensure safety, reliability, and efficiency. To further expand on the practical considerations for this scenario, let's address the nuances of motor protection and the broader implications of harmonics and power quality. Firstly, motor protection is paramount. While the 15-amp breaker provides general overcurrent protection for the circuit, the motor itself requires more specific protection against overloads and locked rotor conditions. This is typically achieved through a dedicated overload relay integrated within the motor starter. The overload relay is designed to trip when the motor draws excessive current for an extended period, preventing overheating and potential damage. The settings of the overload relay must be carefully matched to the motor's full load current and service factor, as specified on the motor's nameplate. The motor starter should also include short circuit protection, often in the form of fuses or circuit breaker, sized to protect the motor windings from fault currents. Secondly, harmonics and power quality should be considered. The single-phase motor and potentially other components within the fan terminal unit may generate harmonics that can distort the voltage waveform and impact the performance of other equipment connected to the same electrical system. To mitigate the effects of harmonics, consider using harmonic filters or line reactors. Harmonic filters are designed to block specific harmonic frequencies, preventing them from propagating throughout the system. Line reactors are inductive devices that help to smooth out the current waveform and reduce harmonic distortion. Power quality monitoring can also be used to identify and address harmonic problems. Thirdly, grounding and bonding practices should be adhered to. Proper grounding and bonding are essential for safety and to minimize the risk of electrical shock. The equipment grounding conductor should be sized according to the National Electrical Code and should be securely connected to all metal parts of the fan terminal unit and the electrical enclosure. Bonding jumpers should be used to connect any separate metal parts to ensure a continuous ground path. Fourthly, think about the environmental conditions. The environmental conditions in which the fan terminal unit operates can impact the performance and lifespan of the electrical components. Extreme temperatures, humidity, and corrosive atmospheres can accelerate the degradation of insulation and other materials. If the fan terminal unit is located in a harsh environment, consider using enclosures and components that are specifically rated for those conditions. Fifthly, maintenance and testing should be done regularly. Regular maintenance and testing are essential for ensuring the continued safe and reliable operation of the fan terminal unit. This includes visual inspections, insulation resistance testing, and overcurrent protective device testing. Visual inspections should be performed to check for signs of damage, corrosion, or loose connections. Insulation resistance testing can be used to identify insulation breakdown in motor windings and other electrical components. Overcurrent protective device testing should be performed to verify that the breakers and fuses are operating correctly and that they are properly sized for the circuit. Sixthly, documentation is key. Maintain accurate documentation of the electrical system, including wiring diagrams, overcurrent protective device schedules, and maintenance records. This documentation will be invaluable for troubleshooting problems and for making future modifications to the system. Seventhly, consult with a qualified electrician or engineer. If you are unsure about any aspect of the electrical installation, consult with a qualified electrician or engineer. They can provide expert guidance and ensure that the installation meets all applicable codes and standards. Remember, electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others. By following these guidelines and seeking professional assistance when needed, you can ensure the safe and reliable operation of the fan terminal unit. By addressing these points, the selection and implementation of the overcurrent protective device and associated components ensure a robust and safe installation. The emphasis on motor protection, harmonic mitigation, grounding, and environmental considerations underlines the importance of a holistic approach to electrical system design. The inclusion of maintenance, documentation, and professional consultation reinforces the ongoing responsibility to maintain and improve the system over time. Lastly, let's consider the specific standards that govern the installation and operation of electrical equipment. Compliance with these standards is critical for ensuring safety and preventing electrical hazards. The National Electrical Code provides comprehensive guidelines for the safe installation of electrical wiring and equipment. It covers everything from conductor sizing and overcurrent protective device selection to grounding and bonding requirements. The National Electrical Code is updated every 3 years to reflect the latest technological advancements and safety practices. In addition to the National Electrical Code, other standards may apply depending on the specific application and location. For example, underwriters' laboratory standards are used to evaluate the safety of electrical product. These standards specify the requirements for product design, construction, and testing. Compliance with underwriters' laboratory standards is often required by local building codes and insurance companies. The Institute of Electrical and Electronics Engineers develops standards for a wide range of electrical and electronic technologies. These standards cover topics such as power systems, telecommunications, and information technology. Compliance with Institute of Electrical and Electronics Engineers standards can help to ensure the interoperability and performance of electrical equipment. The National Electrical Manufacturers Association develops standards for electrical equipment and medical imaging equipment. These standards cover topics such as product safety, performance, and energy efficiency. Compliance with National Electrical Manufacturers Association standards can help to ensure the quality and reliability of electrical equipment. The Occupational Safety and Health Administration sets standards for workplace safety. These standards cover topics such as electrical safety, fall protection, and hazard communication. Compliance with Occupational Safety and Health Administration standards is required by law for most employees. It's crucial to consult the latest versions of these standards and to stay up to date on any changes or revisions. Compliance with these standards is not just a legal requirement, it is also a moral obligation to protect the safety of workers and the public. By adhering to these standards, a safer and more reliable electrical system is created. The electrical system will not only meet the minimum requirements but will also incorporate best practices for safety and performance. The selection and installation of electrical components, including overcurrent protective devices, are performed with diligence and attention to detail. Ultimately, a commitment to safety and compliance translates into a more resilient and sustainable electrical infrastructure.